Thank you very much. Good afternoon. And let me start off by just saying what a great honor it is to be here, especially on such a wonderful occasion. And it's fond memories because my connection, of course, is mostly with Umeå. And I've got fond memories of my first visits to Umeå and realizing, I guess, confirming something I'll be talking about today, which is about the amount of pollution we live with, and just breathing the air and looking at the water, being able to see the fish swimming in the water and thinking, gosh, that's interesting. So, it's very fond memories of a beautiful place. And also, of course, seeing this fantastic resource that you have in terms of your trees in particular. Now, I thought I should maybe be writing a talk which is very much biased towards trees as a resource. I will mention them once or twice, but I won't necessarily talk a lot about them. But I think you can read across from examples I'll be giving you to see where the relevance could be applied into this wonderful resource that you have in this country. You have other resources as well, of course, but certainly because I'm in the middle at the moment actually of looking at research that's going on in various Nordic countries, including Norway and Finland, and and I can see the commonality. You're sitting in a very interesting location, which I think should get much more interesting as the future progresses. But really what I'm doing now is I'm going to take you into the world of chemistry for 30 minutes. So at that point, normally people leave the room, because it's a wonderful turn-off, the classic dinner party turn-off. What do you do? I do chemistry, which is normally followed by, well, I can remember actually many years ago winning an award from the Prince of Wales, our future king. And at that point, he said to me, oh, gosh, I failed chemistry O-level. O-level is what you take at the age of 60. And I thought, and he said it with a smile. And I thought, well, maybe that's typical, of course, of many of the problems we face, which is actually there's almost a degree of pride among some of our leaders by admitting they know no science or technology. But I'm going to take you into the world of chemistry, but hopefully in a rather different way to perhaps what you're used to, in terms of thinking more about the resources, thinking about the implications. I want to spend a bit of time just trying to explain to you why it is what I do, why I think what I do is important, what kind of gets me out of bed in the morning, if you like, and also thinking about the drivers for change, why I believe that actually an awful lot of what we do, maybe take for granted, needs to change going forward. I'll then give you a bit of what in terms of examples, of case studies, if you like, of work that we're involved in. And then, I'll just come back a bit to the why and maybe also thinking forward to the future in the context of what it means for the future generations. One of my favorite slides is what I've got here, which is basically showing you a whole range of articles of today's society. So it's kind of, as a chemist, I can proudly say each and every one of those and everything around us, in fact, depends upon chemicals. So I could challenge any of you to find anything in this room, for example, which doesn't depend upon chemicals. Most of those chemicals are kind of, we don't necessarily think about them all the time. They're there, but we don't necessarily think about their significance. So most people would realize, of course, in the context of pharmaceuticals, for example, pharmaceuticals are chemicals. They contain molecules. They contain a range of molecules, actually, but typically, of course, the most important ones are the ones that actually do the job that we want them for. But in terms of the sort of chemicals and the chemistry, there's an interesting challenge there because the manufacture of pharmaceuticals is only about 1% resource efficient. And the industry knows that. They're well aware of that, and they are trying to address it. So that's a kind of a big issue around that industry. You can go into different industries, such as I'll touch on a bit later, like cosmetics, for example, personal care, products that we all use in different shapes and forms. And these are very interesting. They're, again, very reliant on chemicals. They contain many different chemicals. And there the challenge is to deal with actually, well, where do those chemicals come from? I mean, are they safe? Are they completely safe? Because, of course, in many cases, we're applying them directly to ourselves. And also the complexity of the chemicals. So, you can pick up, next time you're in the shower and you're, in the shower, have a look, read the back of your shower gel bottle and see how many chemicals are on there. And the chances are there'll be at least 20. In fact, the record so far I've seen is over 50 different chemicals inside a shower gel. And as I say to my students, can you think of uses for more than half a dozen of those? I mean, what on earth do we need 50 chemicals for when we clean ourselves? So there's all sorts of interesting issues there and challenges there, especially with regards to the resources. And something, again, I'll mention a bit later, the mobile phone and all electronic devices. The complexity that goes into these electronic devices is incredible. The modern iPhone 7, which I must admit, I've always been an Apple fan, and I probably will give in to one eventually. The modern iPhone 7 has got more than half the periodic table inside it. And it's like, why? Do we really need all those elements? I mean, earlier iPhones had half that number. And even then, you'd be struggling to really think of what they're all doing as jobs inside that phone. Wherever you look, there's interesting challenges. A couple of years ago, I was invited to actually a company that actually makes roads. And when they said to me, can you please come and talk to our annual meeting about green chemistry and roads, I mean, that was one of my biggest challenges. I'm thinking, oh my God, you know. But actually, of course, it's relevant. Of course, the road industry, in fact, is another example of an industry which relies on what we have today in terms of resources, especially around petroleum and the petroleum refinery. The road industry kind of takes the stuff nobody else wants. It takes the kind of lowest grade of products that comes from the fractionation of oil and applies that into making roads. So, you know, that's pretty good, actually. It does mean that the petroleum industry actually has very, very little waste because industries like that will take whatever they can get. And then, of course, one of my favorite ones, because I find it such an interesting, almost example, psychological example, is the good old plastic bag, which in no time at all has become cursed. You know, the plastic bag, it's amazing. I can remember a few years ago in Beijing, and I went to the kind of, they just announced that they would shut down, they'd basically ban plastic bags when it came to supermarkets. And the Chinese plastic bag company virtually disappeared over a weekend. And I can remember going into a kind of the equivalent of a 7-Eleven store buying something, and the guy at the checkout looking at me realized obviously I wasn't Chinese, going under the counter and saying, what a plastic bag? Wow, this is prohibition, exciting. And so, you know, it's very interesting. Why by the interesting question is, so what's the real problem with a plastic bag? Is it the resource? It does use petroleum, which of course is not sustainable. That's an issue, but actually it doesn't use an awful lot of it. The manufacturing process for turning petroleum into the plastic that makes a plastic bag is incredibly efficient. It's one of the most efficient chemical applications I can think of. So it's not really that. The real challenge with the plastic bag, of course, as I'm sure most of you realize, is what we do with it afterwards. You know, the fact that the average consumer uses a plastic bag for about 30 minutes, when it's actually, of course, the lifetime of a plastic bag is about 400 years because it's so badly biodegradable. So there's a different issue there. And again, I'll come back and illustrate that as part of my talk. I could spend a long time just talking on this one slide, and I'll must quickly move off it. But this is kind of, as I say, putting chemistry and what I think of as green chemistry in the context of anything you like, because anything you like has got issues in terms of resources, in terms of the way the resources are manipulated to give us the final articles, and in terms of what we do with the articles when we finish with them, when they're no longer of a value to us. Now, of course, also within that, all of that, you've got all sorts of issues around hazards and dangers. And when I said before, people don't like chemicals, of course, they tend to read the bad news stories in the media, and they'll read about things like, you know, one of the worst chemical incidents of them all, which was Bhopal. And we must never forget these things. You know, chemistry is inherently hazardous. It does involve using hazardous substances. It always will. I don't believe we can all, you know, in the future do chemistry using water or something. You know, we will have to continue to use hazardous chemicals. But the way that we handle them is something we can control, and we should be much more careful about. Bhopal was really bad for all sorts of reasons. Again, I could talk a long time about it. But it really came down to the fact that people were working with very dangerous chemicals in a very confined space, very close to a high population zone. They were storing hazard close to a lot of people, and that's something, of course, which we really shouldn't do. So that's teaching us lessons about the way that we do our chemistry. But even today, we can look at all sorts of interesting examples. So here's a bit of chemistry for those who with a chemistry background. But essentially what it's doing is it's taking you through the manufacturing process for making tantalum that goes into mobile phones. So one of those metals from the periodic table that goes into all mobile phones is tantalum. It's kind of obscure. People don't really think about it very much. I mean, if I said to my undergraduates, what do you know about tantalum? They go, I don't know. It's a metal, it's in the periodic table. But it's not really talked about very much, but it's actually critical to the electronics industry. But when you look at it, it's actually kind of, it's a real example of why we need to do things differently. Tantalum is almost entirely mined now in Central Africa because it's cheap. It's the cheapest source, and also one of the few abundant sources in the world. There's also quite a lot in Australia, but it's much cheaper to mine and process in Africa than it is in Australia. The chemical processing that goes on to actually get the tantalum is horrendous. Those of you who might recognize some of the chemicals there, hydrogen fluoride, concentrated sulfuric acid, molten sodium, for heaven's sake. I mean, you know, some of the chemistry there really is, it's the devil's toolkit, basically. There's some really nasty chemistry in there. And then, of course, this is all to make tantalum that goes into a mobile phone. And then, of course, the big issue then becomes, what do we do with a mobile phone afterwards and all the other things that go in there as well. The point is, there's all sorts of challenges in the way that we manipulate those precious resources into making the various articles that we want today. And, of course, an awful lot of it is actually using the black stuff, is using oil. And this is a very interesting situation. I was talking at lunch about this, and as I was telling a colleague at lunch, I was having a big argument a few days ago with a former Conservative MP of the British Parliament and also a very distinguished lawyer about this whole area. Because people will always say, oh, come on, there's more oil. Yeah, there is more oil, actually. If you want to go to the next Gulf of Mexico or the next Canadian tar sands or the next Alaska situation, yes. But the point is, we've taken the easy oil. We've taken the easy source of petroleum. And oil is not just a building block for cars, for the fuel industry. It is the resource for chemicals. Without oil, the entire chemical industry would collapse. People just don't necessarily think about that. There are many different types of energy we can think of in the future. But think about where we can get our carbon from in the future, because carbon underpins everything, really. Carbon is the dominant element when it comes to chemistry, when it comes to materials. We cannot really do without. Where's it going to come from? And it shouldn't come from oil in the future for all the sorts of reasons you can imagine in terms of sustainability and also in terms of processing and all the problematic chemistry that I've mentioned before. So we do have to think differently about the carbon that goes into our future products. But there's more to it than that. So here's a bit more chemistry for those of you who recognize the periodic table, hopefully most people. And this is kind of looking at the periodic table more broadly and saying, well, actually, okay, so, we live on a limited place. We live in one planet, and we're consuming resources. And we have a very linear approach to the way we consume resources. We dig something out of the ground, we process it to make something like a mobile phone or whatever it is, and then we throw it away. So, of course, that is not sustainable. That surely should mean that certain things are going to be running out, and probably more quickly than others. And the answer is yes, it does. So, in fact, what we have highlighted here in red are elements which are running out very, very quickly, within a very short time period. Based on known reserves and based on our current rate of consumption, we will run out of an awful lot of elements. And by the way, these ones here are the basis of the electronics industry. Without those, there will be no more computers, TVs, mobile phones, etc. And of course, people are beginning to wake up to this. This is quite a new recognition. This was only first published about 5 years ago. And the EU is reacting. The EU now has a critical element list, which identifies many of these elements and basically says we need to think again about how we use them, because they are running out. And also, by the way, you won't find many of these in Europe. Europe does not have a lot of mineral reserves. These tend to be located in places like Africa, in Russia, in China, in the Americas, not a lot in Europe. We tend to be importing an awful lot of these things into Europe to feed our industries. And they are becoming increasingly scarce. The ones in lighter colors appear to be less of a concern. These are all what we call the rare earths, rather ironically. They're mostly in China. And up here, by the way, just one worth mentioning as well, because it's a bit deceptive. Lithium is yellow. It really should be darker now. The trouble is the state is changing all the time, and it's always out of date. Lithium we are using increasingly in things like hybrid cars, in things like wind turbines, all sorts of applications that we've never considered before. So we're also changing the distribution of usage of different elements as we change our technologies. I'll come back to that again a bit later. So we're running out of resources. The key message from this so far is the resources we use to feed all the industries we have to make all the articles I showed you before and many others are running out of resources. That will happen, and this century is going to be a very interesting time because of that. And we also then have this fundamental way of manipulating those precious resources, which is not terribly clever. So as a chemistry student, you would teach our students that actually what you do in chemistry is you put sort of stuff into a pot, you mix it all up together, and you make something. And you measure how much you make and say, okay, we call that yield. But of course, what we rarely talk about is the other stuff, which is the waste. You never just make what you want. You always make other stuff. And that other stuff, of course, we tend to say is waste. And in the lab, in the teaching lab, of course, they have waste disposal bottles. That's very convenient. And occasionally students are bright enough and inquisitive enough to actually ask questions about where do they go. And when you do challenge them with this, they do start thinking a bit more about it. But on the whole, we've been very bad educationally at actually making our students aware that, in fact, there's far more to a process than just the one thing that you want. You've got to be looking much more holistically to really see it seriously. And of course, the result is that this, along with other stuff, ends up as waste. And this is, in a way, the chemical reaction done by the student in the lab is typical of the way we behave in society, which is we have this very cavalier attitude towards what's in fact a very precious set of resources, and also the manufacturing of those resources, and the use, of course, of the articles downstream. We throw an awful lot of stuff away. And as you can see, of all the resources we consume to make goods, just in the manufacturing process, 80% ends up in waste. Even before it gets to the mobile phone, or it gets to the clothes you're wearing, or the furniture you're sitting on, even before it gets to that stage, 80% of the resources are thrown away. We are so inefficient. We cannot surely continue like that. And actually, when it comes to, say, recycling, people say, it's okay, we recycle now. We've got all these nice recycling bins, and people talk about recycling. People talk about places you can take your old computer to and all sorts of things. Surely we're doing better. Sorry, we're not. This data, which, when you look at the data again, element by element, to see what are we recycling, the answer is not a lot. The only elements we're recycling significantly are a few around here. Precious elements like gold, silver, platinum, palladium, but the vast majority, including, again, most of those key electronic elements, all of the rare earths, all of the ones down here, we don't recycle at all. Less than 1% we actually recycle in the world. It's like plastics. People talk about recycling plastics. The reality is we don't recycle very much at all. We're just not very efficient for all sorts of reasons I can't go into now, but we're not very good at it, really. We have to take this whole thing much more seriously. Simply putting something in a bin, we've tracked stuff that's called recycle in the UK. We follow stuff and see where it goes. An awful lot of it doesn't get recycled. It ends up at a landfill site. It's burned. At best, it gets shipped somewhere else, you know, out of sight, out of mind, to make it somebody else's problem. This has to change. And, of course, a lot of the stuff that we don't even track ends up, of course, causing us tremendous concerns. And, I mean, I think one of the biggest illustrations, if you like, of our very poor attitude towards resources is to be seen in the sea now. And I'm sure you've all heard about this. It's now become, again, big news in recent years. The so-called Pacific Air, but also now visible, by the way, in the southern hemisphere as well, is this enormous amount of plastic waste which is accumulating in the oceans. And it's interesting for all sorts of reasons. I mean, the size of it's phenomenal. Look at the map there. I mean, this is the west coast of the USA. This area is larger than Texas. It's an enormous area. Another big one developing there. As I say, there's more and more developing in the southern hemisphere as well. You can't see it. It's microplastics. These are not necessarily, by the way, the microplastics you're reading about now, in terms of those we deliberately put into cosmetics, which is also a bad idea. It's ordinary plastic, like those plastic bags again, that's been broken up into very small particles by ocean currents and so on. These are accumulating and, of course, causing direct devastation in terms of the life, sea life, but also, of course, creating a real... We don't know what it's doing, actually. We're not really sure. The long-term consequences of this are still to be discovered, but they can't be good. And again, as I say, it does represent how very cavalier we are when it comes to our treatment of resources. So all sorts of reasons we need to do differently. And of course, to me, it's all about, well, on one hand, I'm saying the resources are a real problem. On the other hand, I'm saying the waste is a real problem. Well, I mean, the resource becomes the waste. The waste was a resource. So why can't we think about the waste as being a resource going forward? And this is really the kind of mantra that we are involved in my centre at York and beyond, trying to treat those fundamentals, the waste streams we have now, as future resources. And a lot of it's based around biomass, which, you know, is what's biomass? It's the stuff that nature provides at a regular... It's us. So when I challenged students recently, we have a wonderful multinational crowd of students, and when I said to students, come along with an idea for a sustainable source of biomass for the future, and one of my Chinese students stood up and said, old people, which is true, of course, it's true. We are a source of biomass, and maybe in the future, when you leave your will, you can say, I'd like to become, name your chemical, and we'll help get you there. This is just a little cartoon representation to try and show you what we're trying to distinguish, because a lot of this comes down to the nature of the carbon, bio-based or fossil-based. And of course, a bio-based carbon atom, the idea is going into the future for a truly sustainable source of carbon, that we can have carbon coming in from the atmosphere, being reused or being recycled, or ultimately, of course, if it gets into the atmosphere, it can also be renewed naturally as well. So this is the kind of circular economy. Simplified, I realize, oversimplified, yes, but it gives you an idea. and certainly distinguishes it from fossil carbon. Fossil carbon we could use again, we should use again. Fossil carbon we should be able to reuse and recycle, but it can't be renewed on a reasonable time scale. And to try and get this forward, of course, there's all sorts of around not just the science, but also standards and all sorts of interesting, with Europe leading the way, which I think is great. The USA is beginning to follow. Other countries will follow as well, to try and get the whole thing properly standardized. So in the future, when people say it's bio-based, it's green, we know what that means. It is underpinned by some very tough legislation. And you have to be careful. Just because it's bio-based doesn't mean to say it's green and sustainable. Palm oil, of course, is a very famous example. It's really easy to a chemist. Palm oil is wonderful. It's chemically quite simple compared to most other types of biomass, but we know it causes potential devastation when it comes to the local environment. We should be thinking instead, again, about waste streams that we can get a hold of, which are much easier. I mean, so we're very keen, for example, on cereal straws. From cereal straws, you can extract all sorts of interesting chemicals. And there's a nice link to the previous talk, including insect semiochemicals, and also chemicals that go to the cosmetics that I talked about before. There's also all sorts of interesting marine waste, and chitosan, the second largest biopolymer on the planet, which is being turned out by nature in huge volumes all the time, is hardly utilized at all. But we know it's got some really interesting material properties for some of the applications illustrated there. All sorts of different types of waste can be applied and focused into the sort of chemical and material feedstocks that I've implied we need to have in the future, including, of course, as I referred to at the beginning, forestry waste. One example that we're very keen on is taking food supply chain waste, because there's an awful lot of food supply chain waste. And we also are very interested in mapping and seeing where it is in the world, because often when you say to industry, I think you should be actually using one of these waste streams available in enormous quantities. The UN reckons 1.3 billion tons of edible food waste and about 3 billion tons of inedible food waste, like shells and stones and peels and so on. Why don't you use that? Of course they're going to say, where is it? Can we get a hold of it? And one of the examples we've been most keen on, this is just showing you how our mapping is helping to identify regions and what's present in certain regions. But one of our favorites is around orange peel, because we thought the world needed to do OPEC. And this is all about saying, okay, actually orange, we grow 100 million tons of oranges every year. We squeeze an awful lot of them to make juice. What do we do with the peel? And the answer is not a lot. So we're working with a company now who's trying to find, okay, so where is the orange? Well, actually, probably not in Europe, although we process a lot of oranges. The biggest sources are actually around the world in places like Brazil, to some extent South Africa, North Africa, and China and India, again, are interestingly large sources. And this, of course, the orange peel is, in fact, full of chemicals. So, again, a nice link to the last talk, which mentioned limonene. When you peel an orange, you can smell the limonene. Limonene is a really interesting chemical. It's got fabulous properties for all sorts of applications, including as a solvent. And you've also got pectin in there, which can be used for food thickening, for low-fat foods, for high-end cosmetics. All sorts of interesting things can be taken from citrus waste. And this, I think, is an example of the sort of future industries where you can actually symbiotically take the byproducts from something like the food industry and get added chemical material value from those and really boost everyone's business together. It's a classic sort of win-win situation. The technologies we're using are various. I'll just mention one briefly now, which is our good friend microwave technology, because we love microwaves. Have got, of course, a great history in food processing and so on. Less of a history when it comes to chemistry and chemical manufacturing, but that's getting better all the time. And we're working with all sorts of different scales of microwave processors, which we can actually use to get some of those chemicals out of things like citrus peel and cereal straws, and, of course, also woody residues, as we're doing now in collaboration with your university. Just briefly running through a few more examples, not necessarily connected, but they are in a way, because they kind of illustrate examples of what I've said before. Solvents, which is a huge challenge with regards to applications. I won't dwell on this, but basically industry like pharmaceuticals uses enormous amounts of solvents, and they desperately need new ones. Now, the drivers here are partly resources and also partly toxicity. An awful lot of solvents we use today are very toxic. We need green and sustainable replacements. And what I wanted to mention, because it links nicely into your resource here again, is something we've been doing a collaboration with an Australian company, which is a molecule called styrene. And you can make this wonderful solvent in only 2 steps from wood, from biomass. And in fact, the first pilot plant is now almost operational and being built in Tasmania, another interesting place with a very large amount of sustainable forest. 20 million tonnes a year of forest is available for the paper and pulp industry. Paper and pulp in Tasmania is struggling to survive. So we have now built a pilot plant inside this facility in Tasmania, which is making this new solvent. A new business, which the paper industry loves because it gives it a new business. It also provides a new green solvent to replace a lot of toxic solvents on the market as well. So again, a classic kind of win-win situation. I don't see why you couldn't have that sort of business developing in a region like the north of Sweden in particular. And just going back briefly to the metal story I mentioned before, and as I said before also, metals, of course, are being used in more and more different applications and therefore causing all sorts of issues with regards to sustainability we didn't necessarily predict. And this is just giving you some of the places where actually, from a waste point of view, let's not go to the virgin ore all the time. What about the waste streams from what we're doing today? Because there's metal waste all sorts of places, in the mining, in the electronic waste, of course, is an enormous source, in roadside dust. We still spew out an awful lot of metals from our exhaust pipes when we drive our car because the catalytic converter is not operating fully efficiently. All sorts of interesting sources. How do we get those metals? How can we capture the metals, which at the moment are just pollutants, but could, of course, become a sustainable resource for the future? And one of our favorite projects is called Phytocat. It's all about using plants which are natural scavengers of metals. Some plants scavenge enormous quantities of metals inside them, and we can use that to actually get some of those metals back. So we're using plants to capture waste, in particular around metals, and the metals, of course, themselves can be very valuable. We've got other ways of doing it. We have our so-called Starbond technologies, which are based, again, around things like citrus peel, turned into porous solids that can capture metal waste streams selectively in many cases. But again, they represent examples of taking biomass in different forms to actually capture, in this case, metals that can then be used to make a more sustainable metal industry going forward. The last example I've got is just something that's so different, because the nice thing about doing what I do is you never quite know what's going to come up next. And we were approached by Veolia, the big French waste company, about toothpaste. And we thought, oh yeah, toothpaste? Did you know, in the UK alone, we have 50,000 tonnes a year of waste toothpaste in the manufacturing process. It's not you squeezing it down the sink. It's in the manufacturing process. And it's like, what do we do with all this waste toothpaste? And the challenge there to our guys was, okay, well, what are the chemicals in there? How can we get them out? Can we use them for something else? And the answer is yes, you can. It's full of, for example, silicates you can extract quite easily, and they can then be turned into catalysts that can be used to catalyze all sorts of different reactions. So, you know, you never quite know what's going to come up next in terms of an interesting waste challenge, but guarantee all wastes are interesting. They all contain resources we should and could be exploiting. I'm sure many of you know where York is. I won't dwell on these too much. It's a lovely place to work. And the Green Chemistry Centre, where the boys and girls, and there's a picture of them, doing the key work, are based. And we have, our philosophy really is taking the best ideas and nurturing them through towards scale. We have a development centre which takes some of our best ideas, like the microwave technology, and tries it at a larger scale to prove to people, yes, you can do this at larger scale. You can make larger amounts of stuff for testing and applying and so on. Of course, a master's program, very important to us to bring in our feedstock, which is young students coming in from all over the world. And we have our mascots, our green frog, of course, being green. He's an obvious mascot, who occasionally becomes human. So Jenny, one of our students, occasionally dresses up in the frog outfit and is brave enough to do that and go out to schools and museums and all sorts of places, shopping centres, and try to get the message out there that actually everything, what I said to you, everything we use is chemical-based, but the chemicals we use are themselves not sustainable, and we do need to think about things differently going forward. And it's global, it's wonderful, it's international. Wherever you look, green chemistry, sustainable chemistry is being recognized as something we need to do more of. And this has all been happening since I started at York, certainly even since I became a director of the centre. Most of these centres are new within the last few years, which is great. And just one final thing here, talking at lunch about careers and about attracting students in to do some of the science and technology areas, we do find this is a fantastic area to really attract the brightest. This is an organization we call NESI, which is about, as you can see, bringing people together from different disciplines. They're not all chemists. We've got engineers, physicists, biologists, and even people outside of science and technology. But they all recognize the same thing. They all realize that we do need to do things differently in the future, and that they've got the skills and interest to actually use those skills, to actually help move us in a more green and sustainable direction. Thank you very much.